purpose of this lab is to observe and model the motion of a mass that swings while oscillating on a spring that is attached to a fixed point, and to observe the energy changes of the mass as it swings. The model in this lab is an object attached to a spring that is released from a point, causing it to oscillate and swing. This model was then simulated in a glow script code, utilizing Newton's second law to draw out the motion of the model and to observe the energy principle as well. Overall, the main result of the lab was that the computer model predicted most of the object's x and y positions accurately, except for a slight offshoot in both directions due to the limitations of the types of forces that the total net force included. The model also proved the accuracy of the energy principle, in which the total energy change was 0 when calculated by the code. Before observing the experiment and creating a coded model, the fundamental principle behind this experiment needs to be addressed. Our experiment relies on Newton's second law of motion. The reasoning for this is that we are attempting to predict a set of positions and velocities given a net force and initial position and velocity. Based on the Newton's second law, we will be iteratively predicting the object's motion and position through the following two equations, using the net force calculated from gravity and the force of the spring that are acting on the object. These iterative positions and velocities will be then used to calculate the total energy of each position using the formulas for the kinetic, gravitational potential, and spring potential energy, which will be added up for the most particles' total change in energy, as represented by this energy of the system as being the sum of the kinetic and the total potential energies of the system. The system of this experiment is the object, the spring, and the earth, making the surroundings to include nothing. The positions at different times were modeled through the tracker program by tracking the position of the center of the object throughout the time frame. The initial position was obtained to be negative 0.100 in the x direction and negative 0.63 in the y direction. The initial velocity was set to 0 as it was dropped from rest, and the mass of the object was given as 0.402 kilograms. The following set of x and y positions were obtained from the tracker program, which were then used to form the model in the code as a CSV file. The initial conditions of the objects from the previous slide are set in this region of code. The spring constant was obtained from the oscillation period from the position of the object observed in the tracker program. The relaxed length of the spring was then obtained from setting a static equilibrium between the gravitational and spring force, then calculating the relaxed length given the knowns of the mass, gravitational constant, spring constant, and the compressed length of the spring. These initial conditions were used to find the total energy of the system using the kinetic energy of the ball, gravitational potential energy, and the spring potential energy from these calculated values. This while loop was set for iterative calculations as the object oscillated and swung over the time period of 9.402 seconds. The net force acting on the ball was calculated through the gravitational and spring force acting on the ball and summing them together. This net force was then used to calculate and update the velocity, then the position of the ball according to Newton's second law. These new values of position and velocity were then used to calculate the total energy change of the ball by determining each of the kinetic and potential energy of that new calculated value and calculating the difference between the new values and the initial values to calculate the total energy change of that time interval, and this iteration was repeated over the while loop. The delta E calculated by that while loop was obtained in this result of code. The kinetic and potential energies of the system was plotted in this chart over the set time interval, which shows an oscillating pattern that corresponds to the object motion on the right. The delta E, represented by this orange line, is shown to be 0, which proves the energy principle that the total net change in energy of a system is 0. Overall, the model mostly predicted the object's motion accurately, except for a slight deviation in the prediction of both the x and the y position, as represented in this chart on the right. To conclude, Newton's second law was used to model the motion of an object on a spring that swings and oscillates, and the change in energies of the object was modeled to verify that the energy principle was applied. Some sources of error in the prediction of the model's motion could be the absence of the drag force for the swinging and the oscillating motion, as the error can impact both types of motions and thus the accuracy of the x and y positions of the model. What does it mean? The energy principle was satisfied in this model system as the delta E, or the change in total energy, was 0 as per the conservation of energy and the energy principle. The period of oscillation calculated from the x and y positions of the object were calculated to be 1.615 seconds and 1.52 seconds respectively. The oscillating period of the x direction could have been slightly longer than the y direction due to the swinging motion of the object. Thank you for your time in watching this video.